Another draft science presentation. Would like to make these sort of videos that are start to finish, but it's very hard to do. I need to do that in writing, I suppose, and well, I know I need to, but just don't find it charming at the moment. And so it's just why am I making these videos? And then take that question and the full answer in these next few videos, I hope. Now the one's titled this way, I guess we'll just title it Video 1. This is the first video to watch, and I'm already wasting some of your time, so I'll get to it. Conventional physics, and we're talking about physicists, scientists, and these are people usually too connected with being in something called the skeptic community, and but they don't seem very skeptical of anything they propose to exist. And they don't need much evidence at all to go for it. So just a tiny indication, one fossil out of place, and God does exist. Little fringe experiments don't equal what the other experiments equal, and yes, they're ready to jump ship and say, no, men lived with dinosaurs or something, because there's a fossil that has a footprint of a man in it with a dinosaur footprint. Therefore, we have all the proof we need, and we'll believe in multiverses, and we'll believe the simplest things in the universe have all kinds of complex behaviors, and that everything's made out of a whole bunch of complex anti-particles. So they'll call themselves something like a particle physicist, and then they'll believe in something called an anti-particle. Kind of an oxymoron. So they don't seem very skeptical, and they certainly don't seem very scientific, and they really just don't care about having the right answer. They just care about any answer that'll do if it works. So, in 1 minute they argue against religion because it's just a convenient pile of crap, and they fall for the same thing. And give me the quick, easy answer. The now answer. I don't want to wait for evidence to compile. I don't want to have to prove the case. So that's what got me into this, is that's what it has every appearance of being. The real simplest thing that got me into it is just that the answers they have fallen in love with are just so silly. The Copenhagen photons with radar, and then we'll make a new universe every time a photon crashes into something. A new universe is created. I mean, they're just on their face insanely extraterrestrial, having nothing to do with any kind of rational confinement of imagination. They might as well tell me that, Horton Hears a Who is a physics book, because it's almost that bad, or worse. I mean, look, they have particles that jump into the future, have interactions, they borrow from the future, borrow energy from the future. I mean, it's just so bad. So anyway, that's what got me into this. And just the idea that, no, there's got to be a real answer, because those certainly can't be the real answers. Even time dilation, this forever force that somehow a mass just instantly creates this I can pull everything into me. The pull force idea, even in itself, is, if you had to choose one, it's the wrong choice. Just kind of obviously, the push is so simple. Why go for the pull? So all of these, they have lots of loose ends. So they're not either. I can't even split ends. I mean, just ends. Two ends, no connection to anything real at all. Kind of entanglement, all kinds of things that are just, they don't make sense on the surface, and then the more you pick at the evidence, the least and least reason you see to believe in it. And again, it's the whole lack of, they have these fundamental principles in physics, conservation of energy and momentum, and yet they don't have to have any of that conservation, because they just create virtual things that just live for a little short temporary amount of time, do what they want, and then disappear. So they go into an equation and pop out of the equation, and therefore they don't have to account where to come from. How did it get there? None of that is necessary. So yes, that's what got me into this. And I don't seem to have something called a lighter here. Well, I'll through this thing. It's not really a lighter. It's a flamethrower. Okay, that'll do. Yes, I have cigarettes. Every 2 months somebody sends me cigarettes, so I do enjoy them still. Very, very much. Yeah, so yeah, so that's what got me into it, and so you start, because you get into it on these fundamental, they point to, well, how do you explain this experiment, the two-slit experiment, and you do some research, and you find out some different things, and you find out, well, the single-slit experiment came long before, and it has all the features of the double-slit except for one, and so why didn't physics start there? Why were they amazed by the Young experiment, when the Young experiment didn't really demonstrate anything that Newton hadn't already demonstrated as a phenomenon? That kind of thing. And you start picking at this stuff and you see that their math doesn't exactly, they talk about it as if it's the most perfect and beautiful math in the history of mankind, and you find out, no, it's kind of a simple equation. There's only one factor that matters, this sine theta angle, and that there's lots of ways you can figure out a mechanism that creates an angle. That's all the experiment does. Is the experiment sits there in front of you and has proportions. It has lengths and distances before you even put a photon into it. And you can figure out before you put a photon into it, yeah, there's one thing that's going to be critical, and that's this angle thing. And the rest of it's going to just depend on where the photon goes. And there's no need to make up a whole notion that the photon doesn't know where it is, and it's some sort of probabilistic orb, and it's all that. You don't have to do all that stuff. You can come up with a mechanical and a physical explanation without resorting to, notions that physics isn't physical. And that, Feynman said different things at different points in his career, but he seemed, in the 80s anyway, to be somewhat convinced that photons were discrete particles, but that that the universe itself didn't care about some sort of cause and effect, that it was in itself intrinsically probabilistic, and there was just some idea that, yes, it's really rolling randomized dice, that somehow the universe pulls out of its pocket real random dice and rolls them. And even that is just that seems such a leap, a stretch to, depart from a cause and effect universe. So, what I discovered in playing with all of these things that existed, these truths that we know are the good evidence versus their speculation and their wishful thinking, maybe, is that you can't explain the good evidence with a mechanical model, with discrete, as small as you can see anyway, bits that don't need a whole bunch of complexity in their function. So you have something called like a force bit that would be something that moves the speed of light. So all the forces have in common, all the known forces, a limitation to their speed. They don't move instantaneously. There's no force we know of that's instantaneous, except for entanglement. And again, that's not a force that we know to exist at all with any hard evidence. And that the lack of instantaneousness is centered around a speed of this, what we call the speed of light, what they call the speed of light. And it's really the speed of force, because all the forces behave exactly this way, have this same consistent property. The other thing all the forces have is that you can't divide them into smaller force. You can't have a half a force or a third of a force or any of that kind of thing. It's all or nothing. You either get forced or you get no force in terms of its energy, quanta. It comes in clumps, as Feynman would say. And that's pretty hard truth, that force is a clump. I call it a bit. I think that covers it. So I wrote down over here just little stuff over here. There's one universe, and essentially it's the small universe that's the universe. That's where all the action really is. I mean, yes, the big universe has big stuff moving in it, but it's only moving because the little stuff told it to, so to speak. The school of fish is an illusion, so to speak. It's the fish that are doing all the action. And what the school does, yeah, okay, it's doing something, but it's not really doing something because it's nothing without the fish. And the sun and the moon and the earth and all this stuff and us, everything is nothing without the fish. Okay, without the little universe is what really is making it happen, and the laws of the little universe are the only laws that really exist, and the rest of them are just some sort of something you can approximate. That the school of fish, for example, it can't go faster than any one of the individual fish. It has certain rules as a consequence, but those rules are just byproducts of the rules that exist for the fish. Now, some people might mock that as a too simplistic a way of looking at, making analogies to fish, a school of fish. But I would argue that the real universe is that simple, that it is made of bits that have very few properties, like a photon, for example. It moves the speed of light, it has a consistent weight or size, and all you really can do is change its frequency, change how far apart the bits are, and you'll change its effect just as you would change another simple analogy, just as you would change the effect of bullets based on how fast you shoot them. You can break something better by shooting bullets rapidly, or you can knock something over by shooting bullets at a speed. And so there can be an effect that's more than the cause, in the sense that the changing distance doesn't on its face have any obvious implication, except, well, you could fit more bullets in a smaller amount of space or time. It has little obvious things, but it doesn't say obviously this is a huge difference. But the huge difference is the thing you're hitting is in a state, and that state is disturbable. And so that's why some kinds of light affect electrons more than other kinds of light. It just has to do with the speed and how much the electron is moved, and it has to move a certain amount, faster than, say, rebound speeds. This would be a simple, I've come up with numerous examples of how you can explain a phenomenon just by understanding the condition. Well, sorry. The sound should be a little better. Yeah, I'm getting a byproduct, a cause and effect. Somebody's sending me a little computer upgrade, so hopefully, but yeah, you can only hope, because still don't know what layer of Linux is failing when it comes to doing sound without distortion. Anyway, with enough volume, it just seems weird. Anyway. I mean, anytime Windows does something better, you have to say, well, that should never happen. Windows should never do anything better. But anyway, all right. So let's say this was an electron, and the idea is you can hit it and it moves, but it wants to move back. So if you don't hit it quick enough, it moves back. So the quicker you hit it, then you can get it pushed out of, say, some envelope of space that's relevant. Some place it's stuck in. But it's going to stay in the stuck place if you just hit little hits and then you let it go back and then you hit it again and then let it go back. You're never going to hit it out of there. But if you bring two things in quickly, then you'll hit it out. So that's a simple analogy, but it explains the ultraviolet crisis, and it explains why some light, although it's the light itself, the little tons are made out of exactly the same stuff and have the same force potential, that they have a different effect. Alright, so the next, so just understand the small universe, the little stuff, is where everything's really happening. And fundamental to my my theory, my speculation about what a more reasonable explanation is that the universe is just full of all these little bits, these little force bits moving the speed of light. And some of them we can see because we have a detecting mechanism, like for photons, for visible light. But a ton of them we don't see, and they pass right through us and right by us and do things, and we have no idea they're even there. And I would just argue there's a lot more of that, not their stuff, the stuff that isn't even on the electromagnetic spectrum, because it doesn't come at a frequency. It just happens. They're little individual bits, and we don't have any detector for them, except the fact that, when you consolidate a bunch of matter, that those bits allow you to have something called gravity, that they're actually causing that effect with their impact. So you can imagine how much light you would have to hit this with to move it. I mean, it would take a ton of photons to move this thing, and yet it's moved by these little bits. So that's some idea of how much the ones without a frequency, the ones that aren't organized, is so much denser than the amount that we interact with, like light. So much more energy. And that if you take that, well, we'll pay attention to the list a little bit. So there's one kind of interaction, and that would be the force bits. So anything moving the speed of light. So this would be the magnetic force is really just a filtering of the gravity force. So it's gravity in, segregation of the force, and we call it magnetism out. But it's really gravity. And gravity itself is really just these force bits that fill the universe. They create a constant pressure, and when you put two things in the field of that influence, they will end up absorbing some of the pressure and creating low pressure between them, and they will move into each other. And they call it Mach gravity, but it's, the idea is you can make a very good model of gravity using a particle theory, and that's been a truth for a very long time. Now, it creates a couple of paradoxes or problems. Well, really only one that means anything. All the rest can be explained as just byproducts of the inverse square law, circular, all kinds of stuff like that. But that's the idea of motion through this density of particles would mean that any motion would create something called drag or friction, and you have to explain that. I have offered explanations for why, because this is what you're really interacting with is stuff that's already made of stuff moving the speed of light that's just caught in traps, and stuff that's not trapped, okay, that's moving freely, but it's all moving the speed of light, and you can never have an interaction at any speed faster than that. So in a sense, you can't create drag. But anyway, I have videos going over some of the arguments that could be made for possible explanations. Anyway, alright, so there's the one kind of interaction, and so the matter bits, we don't even have to define them, in my opinion, to understand the universe, because the universe is really about what the force is doing to the matter, not really about what the matter is doing. So you could argue the matter was nothing. It was just a conduit. It's just a thing like the force bit can't interact with the force bit. They don't interact with each other. They can only hit the matter bit. And so you can make the matter out of anything. It really doesn't matter as long as you just have that simple rule that force can hit matter. Force can't interact with force. Now the argument that force doesn't interact with force is that's the evidence for that is all over physics. In all of the manifestations of force, it's clear that forces don't bounce off forces. So two magnets aren't bouncing, their force of each other isn't bouncing off each other. The force from one reaches the matter of the other, and the force from this one reaches the matter of this one, and that's when the force is engaged. But the forces themselves don't interact first, and it's like light doesn't hit light. You can't bounce two light bulbs off of each other, the photons. That's probably not the best place to put that. So let's see if I need to say anything more about the one kind of interaction. So just to understand that all the velocity things have, all their movement, all the stuff they do, really happens because force pushed them into that position. And that if they're going to maintain it, they have to either capture the force, that is, the thing that has momentum in a certain way has to kind of go into the thing and stay in there, kind of always pushing in that direction. So when the Earth moves towards the Sun, what the Earth is really doing is capturing energy going towards the Sun. And that energy is still in there. It moves around, but it's still in there as a bit of momentum in a direction. And when it captures it, it means that this didn't hit the Sun. So now the Sun's not feeling as much pressure from one side as the other, so the Sun does the same thing, and it captures energy going towards the Earth. And that's the nature of the induction that creates gravity. And that's what every force, that's what matter bits are doing. So matter bits are basically saying, I'm comfortable, leave me alone. And force either keeps hitting them to keep them moving, or the force is absorbed by the matter and stays in them as an influence. But that's why matter bits move, is because of force hold them to. Now, some of them can't capture it. Like an electron, for example, I don't think you can capture momentum, so you can't shoot one far away. You can't make one go a long distance. All you can do is keep pushing it. So you have to have a ray behind it, a force that keeps it going. So you have to keep a voltage behind it. The voltage keeps saying push, 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 push. And as soon as you turn the voltage off, the electron stops. So you can't give an electron free momentum. And so in gravity, for example, an electron would move 10 meters per second, but it would never go any faster. It would never absorb force and then add to it. So it would just be the constant force would be the only speed it would ever have, is what the constant speed is, the constant force speed. So it can, so to speak, accelerate, but it can never gain anything called, for example, velocity, its own velocity, durable velocity. And so it's only an arrangement of protons and electrons that allow you to create a force mechanism. That is, the force will be between the proton and the electron, and another proton and another electron, and the force will be moving between those objects, and it can move with a bias. That is, it can have more force going one way than force going the other way, and therefore have motion in directions. And that's what happens when you give something velocity, is you change the orientation of the force inside of the object, meaning that it has a bias in a direction. It has more force going one way than it has the other way. It has more, so you always have to remember the force doesn't mean anything until it hits matter bits. So the force is interacting with more matter in one direction than it is in the other direction, and therefore the matter bias is in a direction. You can go back to a fish analogy, and then you'd have to say, you have to understand that the fish aren't moving by something internal. They're moving because there's some little smaller fish that tell them where to go. And without the smaller fish, they don't go. But you could understand that the smaller fish could have a bias, and then that bias would be the implication would be the bigger fish would be moved by it. Alright, all force bits have the same speed. So we sort of already said that, and I guess I don't know what else to say about it, except it should have been a glaring fact in my opinion. So this is one of those things where you say, well, why didn't physics pay attention to that? And why is physics saying something like the speed of light, when light is one tiny, just a tiny bit, visible light, is a tiny bit of what we know to be force in the universe, and yet we say the speed of light. So that just seems like an obvious, circumstantial, like, okay, yeah, human beings anthropomorphized the universe, made it humanish, and they emphasized the things that are human relevant and ignored the bigger picture. Now you could see them doing that in the past, and that's why there's this bias. But it is a huge bias, and I think it distorts perspective, and it allows them to separate these things and say, well, this stuff, this electromagnetic stuff, what does that even mean? Electromagnetic. Because that's creating new force fields and stuff, and they haven't ever explained any of that stuff. That's where they make up virtual photons and stuff. As soon as they say the word field, they'll never give you a detail, because the detail won't have any practical reality. It'll have some virtual reality, some made-up story reality, but nothing tangible, nothing evidential. Just a story. Very hard to prove the non-existence of the talking three bears beyond just saying, I can find you the guy who made up the story. And so you can sort of see that in the history. The history had a bias, we all understand it, but they don't fix it. And they don't say, there's no emphasis pointing out that what it really is the speed of force. And if you kept hearing about the speed of force, then you might be more, your brain might tend to think, well, why are we making gravity bent space when it's going the same speed as magnetism? And we don't call it bent magnetism or bent something. We understand that might be made out of rays of energy. So if you said the speed of force, then you'd have to sort of understand that, yeah, these forces are very related, and they are very much alike, and they have a lot of properties in common. And how can we have completely different mechanisms, quantum mechanics, probabilistic, blah, 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 on one side, and then have bent space and bent time on the other side, completely different explanations, mechanical mechanisms. And, there might be more tendency for people to say, yes, that probably isn't right then. There's too much in common for these things to be completely different abstract mechanisms. Alright, so it's really important to just recognize that all the energy in the universe, the stuff we call energy, or the stuff we call the stuff that makes something happen, all that stuff is moving the speed of light. And anything going slower than the speed of light is because it's absorbed a tiny bit of energy into something bigger. It's like one fish going 40 miles an hour and all the other fish are going 10 miles an hour. Well, when it goes into the school, it can't make the school go 40 miles an hour. It can only make it go a little bit over 10 miles an hour. Alright. All matter velocity is caused by force velocity. So that's another way of saying what I've already just said, is that when matter is just doing a derivative, just doing a consequential division of force. So force comes into it, it has already a state inside of itself, a disposition, and it just adds that new little bit of force and it has to be essentially liquidated over the entire whole. So it's like dye in water or something. You have red dye in water, you put one single particle of blue in there, you don't expect the whole thing to turn purple. So it's always a volume equation, and so all velocities have to be changed or created by sufficient amounts of force, and the forces combined and are interacted in a way they have good math for that. But what's causing it is just the idea that everything is translated between matter and force. So if matter is moving, it's not likely to hit other matter in any real sense. It's only going to likely hit forces. The forces are going to have to, the forces, between the electrons and the protons are the things that are really going to interact. So if we understood that the surface of my hands are covered in electrons, you could sort of understand that those electrons are repelling each other, because when force hits an electron it reflects. So the closer they get to each other, the more stuff that's reflecting between them, and when you get them close enough, the forces will become high pressure in a sense. The little force bits will be bouncing back and forth between the electrons. Electrons won't want to be that close, so they'll move away because they're getting hit by more force, more interactions. And when that matter moves, it'll create force changes in all the rest of the atoms, and then the material things won't be able to go through each other. And there's the effect is really just the matter bits and the force bits, and there's no real matter bits don't hit matter bits usually, and force bits don't hit force bits. And it's always going to be translated. Any action a piece of matter has is always going to be translated to another piece of matter through the force bits. Yeah, I don't know if I said it as simply as I should have, but it's close enough. Alright, two kinds of force bits and two kinds of matter bits. And so you have something called the electron and the electron force, and then something called the proton and the proton force. And I think for 99% of physics, 98, 97, you don't need to talk about neutrinos and gluons and quarks and all of those particles that they've created in accelerators, because they aren't real players as independent things, and I don't think it's necessary to subdivide electrons and protons, because they don't subdivide naturally. They don't fly apart into little pieces and create new electrons or new protons. All that stuff doesn't really happen in any kind of natural environment. And so for most of physics, you can understand that the real players are just electrons and protons, positive charge and negative charge. And their charge is just based on the idea that this field energy, the gravitons, the first little bits come in just two varieties, red and black, you could say. It doesn't matter, square and round. Whatever you give them, two shapes, triangle, squares, it just really doesn't matter. But they have two different, they can be recognized as different by different things. And so electrons, we'll just use black for the sake of the argument, the little black force reflects off them, and so it can give them momentum, but it reflects. And for the proton, the little red force reflects. And then for the electron, if a red bit hits it, it comes out perpendicularly. It doesn't reflect. It reflects perpendicularly. And the same is true if a black or an electron force hits a proton, it comes out perpendicularly. And this simple mechanism creates the ability for two things to attract, because you could sort of understand that all the black force that hits the red things go out, all the red force that hits the black thing goes out, and so nothing can start reflecting. You can't have any perpetual reflection. Now if both of these things were the same, if both of them were black, then you can understand that reflection is just constant reflection. So the closer I bring them together, the more reflections. So the force increases as I bring them together if the forces is the same force that the bits are made out of. If the two bits are different matter bits, then that can't happen. You can't have a increased pressure, because as they get closer together, they just shoot it out even quicker. So the force, it's a drain for force. And that simple mechanism holds the entire, that's everything. Everything that happens inside of atoms is happening because of that, and how that regulates the positions of the bits. It's all magnetic. That's essentially the magnetic force. A magnet is doing the same thing. A magnet's just sitting there, and mixed force hits it. Black and red hits one side, and it only comes out as black at one end. And when the black and red hits the other side, it only comes out as red here. So all the red force comes out of this end, all the black force comes out of this end. So it filters. A bunch of mixed force comes in, and filtered force comes out. So when it goes through, it's essentially changed, or you can just say it's redirected. However you think of it, doesn't really matter. The point is that what goes in is unfiltered, and the magnet is just a filter. And then when you take the two magnets and you turn them opposite each other, so the polarity is opposite, the same effect happens. All the black force coming off of one end goes out of the red, and all the red force goes out the black. But if you turn them face to face, the same polarity, then you get reflections back and forth and reflections back and forth on the two poles, and creates a tremendous amount of repulsion. And so it's a perfectly sensible explanation for magnetism. It just requires the understanding that you have two kinds of force and that you're filtering it. So it's really simple. I mean, very few moving parts here, right? I mean, all you're talking about is two kinds of force and two kinds of matter bit, and the fact that the force affects the two matter bits differently, each kind of force. Now, I have to come up with names for these things, but like I said, I think the simple way to say it is there's an electron, a negatively charged, and that the force relevant to electrons is the electron force. And then you can have the proton, and then the proton bits, force bits. And so light, for example, would be made out of just electron force. So it's segregated. It doesn't have red stuff in it. It just has the black stuff. Just round instead of square. And they're at a frequency. And that's why they have this electromagnetic effect. It's because, yes, it's an electron force. It moves electrons. It's repulsive to electrons, the force of light. And it'll go through a proton and be redirected. So protons can take that force and change which direction it's moving in. Electrons will be pushed by it. Yeah, so it's probably enough for this first video. So we just call it video 1. I think. Keep it simple. So I think I probably have to go into more, if this is the first time you've heard any of this, into the idea of the universe being just full of this force, and it's moving in all directions, and that in such a field, if I could make a universe, it was just little force bits moving the speed of light in every single direction, completely randomized, and I stuck you in the middle of it. The fact is that all the stuff that hits you was heading right for you from forever. Doesn't matter if it's 15 billion light years away, 2 feet away. Doesn't matter how far, and it would look just like a light bulb in reverse. The stuff coming at you and that's why everything's round. That's it explains a lot, and it certainly would explain also, like I said, when you put two things next to each other, you can sort of understand how they would block some of those rays coming to you, and that being shielded from those rays would mean that if they had a pressure to them, you would have to move into that lower pressure. You would. Now the exact process is a little more complicated than just simply being pushed in, because it's more about absorbing energy than merely pushing. Hitting is an absorption, as much as it doesn't look like it. It's basically an exchange. When something hits something, we think, okay, it reflects. It doesn't really. What's really happening is stuff going this way goes in, stays in. So fish going this way stays in, and fish going this way, the wrong way, right, going that way, leaves. So it's an exchange for a fish going this way. Wrong way to say this. It's an exchange for a fish going this way for a fish going this way. And so this is changed. It's not just a reflection. You don't get just nothing here. You get a change, exactly the same change over here. A fish going this way was exchanged for a fish going that way. So this goes this way, and the fish goes that way. But anyway, it's simple physics, but you have to weave it into the entire big picture of all the complex math and the abstractions and all the other stuff they've created. But the basic mechanism of movement is made out of something that simple. Alright, so until the next video.